So continuing on our theme of Abacus Medal or Nonlinear Prize winners, Avi Wigderson won the prize in 1994. He did his bachelor's degree at CS Technion and his had a couple of master's degrees and his PhD in the 1981, 1982, 1983 at Princeton University. He was at the Hebrew University from 1986 to 2003, and since 1999, he's been the Herbert H. Moss Professor at the School of Mathematics at the Institute for Advanced Study. In addition to the prize mentioned earlier, he's also won the Abel Prize in 2021 and the AM Turing Award in 2023. So it's our pleasure to hear from you about the value of errors in proofs, the fascinating journey from Turing's 1936 R not equal to RE to the 2020 breakthrough MIP star equals RE. Go ahead.
Thank you. Thanks for the introduction and for having me. I wish I was there. I planned to be there, but I couldn't, so it will be online. Of course, I'll explain the terms in this long subtitle. I'm talking about proofs and proof systems, and you see on the slide my favorite proof system, but you'll see many more. So it's a story of the evolution of proofs and proof systems within complexity theory in the last something like 30 or 40 years. The plan, I want to get to the value of errors in proofs and their impact on essentially everything, very fundamental concepts that affect science, technology, math. But before talking about errors in proofs, I want to talk about errors in computations. And before that, I want to talk about just this wonderful relations between proofs and computations that's driving this evolution. And maybe the more fundamental thing is to exemplify by this story the methodology of computational complexity, in particular modeling, algorithmic efficiency, the insistence of it, and classifications of problems and computational models in families. There's very long history of the interactions of proofs and computation in mathematics. I'll just give you 2 points in this long road. One is the elements of Euclid, which you all know. People refer to it as a collection of proofs of theorems in plane geometry, deducible from very simple 5 axioms. But if you look at all the proofs, they are all actually algorithms, how to construct certain point sets using just a straight edge and compass. So in this world of plane geometry, proofs and computations are the same. Back to the turn of the 20th century, Hilbert actually believed that this is true about mathematics in general, not just plane geometry. His dream was that truth in mathematics is the same as probability, and moreover, probability can always be determined by a finite mechanical procedure. Of course, as you all know, this dream was shattered, first by Gödel, his incompleteness theorem, shattering the first equation, and then the second by Turing. And I want to focus on Turing's result, because it's about proofs and computations. The main thing about Turing's paper, it's famous for many things, is the definition of what a mechanical procedure is, what an algorithm is. It's a Turing machine. Of course, this had a side effect of creating the computer revolution, but I will talk about math only. So what do algorithms compute? For this talk, they compute decision problems. We fix a set S, like the prime. We are given an input, like an integer, and we ask, is X in the set? Is a given number prime, for example? That's a decision problem. And he defined 2 classes, which today we call R and RE. The first is the sets computable by finite algorithms which always stop. And RE is the sets that are provable, where statements X is in S are provable to finite algorithms. And famously proved that these sets are different. He found the halting problem is something that's really undecidable, cannot be computed by finite algorithms, even though we can verify that a machine is halting if we know the time it takes. Just remarking that we are still struggling with the really complexity theoretic or efficiently motivated analog of this, which is the P versus NP problem, where we just replace finite by efficient and insist in this case efficient is polynomial time. Of course, we study other measures. So it's really the same conundrum on understanding the relationship between proofs, between verification and computation. So I'll start with a few examples about these objects that we are talking about, proofs, verifiers, claims, and so on. More basically, what is a convincing argument to a person in the street, to a mathematician? Let's try to understand. There is a claim, and there are two parties. One is a verifier, which is eager to know the truth or falsity of this, but is limited, perhaps cannot compute it himself. And there is an all-knowing prover, magician, is infinitely clever, knows the answer to all questions, but we cannot trust, cannot take on faith what he says. So he needs to somehow convince us by an argument. So this basically defines what proof systems are. Let me first talk about some classical proof systems you know. Here's the proof systems for the composite numbers. Claims are this number is composite. An argument for it will be two smaller numbers. And the verification is just multiplying them to see if they give the input. And then we decide to accept or reject. The verification, and I'll insist on this again and again, is efficient, is simple, just multiplication. This is general, works for any composite number, and a set of theorems, this proof system has a set of theorems. It can prove only the composite numbers, cannot prove the prime number. And more to stress is that finding the argument, of course, this is what we as mathematicians always look for, proofs for theorem, but finding the complexity of finding an argument for a claim is none of our business here. I mean, it can come out of magic, out of anywhere. We are just interested in the efficiency of verification. In fact, in this particular case, as you all know, these arguments are factors of the given integers, and cryptography today, even the security system, rests on the fact that it's difficult. So maybe it's difficult to find the argument, but we can always verify if an argument is good. Here's another favorite one. The claim is that a particular Sudoku puzzle is solvable. An argument for it is very simple. You just fill in the missing numbers according to the Sudoku rules. So that's what the verifier will do. It will verify the obvious rules of Sudoku and say yes or no if they are satisfied. Again, it's a very efficient process to verify an argument. The set of theorems provable in the simple proof system are the solvable Sudoku puzzles. And there are infinitely many such claims because we can, move to higher and higher sets of statements. In fact, you can wonder whether solving Sudoku is harder or easier than factoring integers, but we'll leave it at now. A more familiar standard classical deductive proof systems are things like piano arithmetic. You manipulate objects, maybe formulas over integers in the case of piano arithmetic. You have a bunch of axioms and deduction rules. And an argument for some claim, which is a formula, is a sequence of other formulas, A1, A2, etc. And verification, again, is a very simple, efficient process. You just check that each one of these formulas is an axiom or follows from previous ones by a deduction rule, which is entirely syntactic. So again, very simple and efficient. Here we have more interesting theorems, of course, like Fermat's theorem, or that are infinitely many primes. But again, it's a proof system, just like the others. And we want now to classify them. What is essential about all these examples, including plane geometry? What's essential is completeness. True claims should have proofs. Soundness, false claims should not have proofs. And again, efficiency should be easy to check, to distinguish between these two cases. There must be an efficient algorithm distinguishing them. Efficient, again, will stick with polynomial time here. That's the complexity theoretic view, which are now formalized, was formalized by Cook and Recha, classifying all classical proof systems. So being more precise, we want a proof system is defined by an algorithm, V, a verification algorithm, that takes two inputs, claim and argument. And it satisfies this completeness and soundness. Completeness means if the claim is true, then some argument makes this algorithm accept. This is the happy case, of course, where we call the claim a theorem, we call the argument a proof. And soundness, if a claim is false, then no matter what argument is fed there to the verifier, it will reject. This is one proof system, one for every verifier V, and we can denote by T sub V the set of theorems of this system. And now, one obvious reformulation of the class NP is simply all theorems, all classes of theorems proved by, verified by any deterministic polynomial time algorithm. This includes all proof systems existing in mathematics. So it has, I showed you examples of some sets in NP like Sudoku or composite numbers. And moreover, if this verification algorithm ignores the argument, then it is solving problems in P. So you have another way of thinking about P and NP as, well, again, proofs versus computation. So this is the end of the classical story. I want to start introducing these errors in proofs, but first I'll introduce them in algorithms, and I'm sure all of you have seen probabilistic algorithms. I'll just run through a one-slide summary of this. We take it as some axiom that nature provides us with free access to randomness. And if we believe this, let's, let's use this resource in algorithms. Let algorithms make random choices. So the distinction is that deterministic algorithm without randomness, if it computes a function, it gives the correct value always on every input. Whereas a probabilistic algorithm with randomness will give the correct answer almost surely, with high probability, but not always. So it defines the output, but it can make errors in particular runs if the randomness is bad. So here, errors are introduced to algorithms. This seems to have been accepted very easily. In fact, the use of randomness in human life is ancient, and we accept that there can be an error. So one point about what high probability means, I wrote here 2/3, namely 1/3 of an error. One reason that this is a good choice is that it can very easily reduce the error arbitrarily by running the algorithm several times and taking majority vote. So you can reduce error arbitrarily. Still, why do we tolerate even an arbitrarily small error? Well, we seem to be able to solve more problems. We seem to have many problems that we have fast algorithms for, which are probabilistic, but maybe not deterministic. That's just the subject for a different talk, whether this is true or not, that randomness is powerful. And the rationale for allowing errors is that, everywhere in life we tolerate uncertainty. Why not in algorithms? Even when we cross the street, there is some chance we won't get to the other side. And so that's the story of probabilistic algorithms. But given this notion, we can now very naturally generalize proof systems because they were defined by an algorithm. This definition in two independent papers in '85 suggested exactly that. Assume that we allow a verifier to be a probabilistic machine. So the same conclusions, the same properties of completeness and soundness are simply required to hold with high probability, can be arbitrarily high probability with amplification, and voila, we introduce errors in proof because sometimes the verifier will make a mistake. Now, this seems very different, especially to mathematicians, than errors in algorithms. Proofs are the objects that's supposed to separate us mathematicians from the rest of the world, this absolute truth. When we have a proof, it should be absolutely correct. And here this is somewhat sacrilegious. Nevertheless, we'll flow with this, see why it's so important. But also these proof systems, we can define for each one, for each probabilistic algorithm V, set of theorems proved by the system, the set of claims accepted by this verifier with high probability. And we call this class IP for interactive, probabilistic and interactive proofs. I told you half of the definition in these papers. Now I'll tell you the other half. What is this interactive business? So let's look again at the classical NP proof systems. We said that the verifier is deterministic, always correct, and the prover supplies an argument. In IP, the verifier is allowed to be probabilistic, it allows to make tiny errors, but moreover, we allow more than a single message between the prover and the verifier. We are allowing them to interact, for maybe the verifier to ask questions of the prover. And after some iterations, decides, again, polynomial time, decides whether to accept or reject. So this is the full definition of IP, this new class of probabilistic and interactive proof systems. You can ask a question about any model. You should ask a question about any model, whether it's reasonable. I think in this case, these people in the audience will agree it's reasonable because we, as we practice mathematics, we are very happy with interacting with others and asking questions and wanting to see more examples or proofs of dilemmas and so on. So interaction is very natural. We are allowing errors, which I said might be sacrilegious. I want to stress that once this definition was on the table, it became a revolutionary scientific notion. I'll give you some taste of this throughout the talk because we'll evolve from that further on, but it's absolutely revolutionary. It has impact on all I talked about, on science, on technology, on mathematics, and various conceptual impacts. I'm going to focus on the impact to proof systems which have paradoxical properties which we don't expect of our normal proof system. In particular, we see zero-knowledge proofs, which are convincing proofs revealing no information, and PCPs, convincing proofs which don't need to be read. Very paradoxical. Moreover, I want to tell you about this meandering journey that leads from one proof system to another from different motivations until we get to this finite MIP star, to the final MIP star I promised in the title. Okay, so what is the zero-knowledge interactive proof system? This was suggested in that paper, which was motivated by cryptography. The formal definition is quite complicated, and I will not tell you, but the intuition is what you think. We want a normal interactive proof system, plus the demand, which looks ridiculous, is whenever the verifier believes a claim, it's learned absolutely nothing else than that the claim is true. nothing else. Now, for mathematicians, or for anybody, I mean, when did you last convince anybody of something without telling them something they didn't know? Doesn't make sense. It certainly doesn't make sense in, cases of mathematical theorems. The whole point of mathematics is learning from proofs of others. We expect to learn from a proof. That's how we make progress. So here we want to make progress in truth without revealing information. They asked this question. They gave a couple of simple examples where simple claims can have zero-knowledge proofs, and the question is whether general claims, mathematical claims, can have zero-knowledge proofs. And a year later, we proved with Micali and Goldreich that it's a universal notion. If you have a proof, a normal mathematical proof, you can turn it into a zero-knowledge interactive proof. This comes with an assumption. The assumption is a normal assumption of cryptography that one-way functions exist. So the proof of this theorem uses cryptography, and we'll discuss this in a moment. But I want to stress in this axiom, the one-way function exists, is something you believe whenever you shop online, so it's not such a big axiom. And everything you can prove in zero knowledge. Very mysterious, and you can think of here, why that's maybe one reason I want to allow a tiny bit of error, at least in practical situations, maybe not in the Riemann hypothesis where something is proved. Okay, so you can have one paradoxical notion achieved with interactive probabilistic proof systems. This had an amazing effect on lots of aspects on theory of cryptography. Let me not go into these impacts. I'll just mention them: the theoretical impacts, practical impact. It was proofs like this have been implemented and are being used in blockchains and other aspects of cryptography. People took variants of it to realms I didn't dream of, physical realms like nuclear disarmament and anonymous DNA testing. But mostly I want to tell you about how this led to new proof systems, in particular this MIP model. Okay, so let's go back to the statement here about zero knowledge, as I just told you about. As I said, this statement came with an assumption, a cryptographic assumption that one-way functions exist. Now, while the whole world accepts this axiom, we in complexity theory always try to reduce assumptions, computational assumptions, to the bare minimum. And we were wondering whether this is possible here. We certainly use cryptography, but is it essential? Well, here's the question, and the answer, like many questions, is yes and no. Yes, crypto is essential. This was proved by Rafael Ostrovsky and me. If you have a zero-knowledge proof for a non-trivial statement, then it implies cryptography. It implies one-way function. So in what sense is it no? How can we dispense on it? And this is something, again, mathematicians are very familiar with. Let's change the model. In this model, it's impossible. Let's change the model. A couple of years after that paper with Ben-Or, Goldwasser, and Kilian, we introduced a new family of proof systems, 2IP or MIP. 2IP is for proof systems with two provers, not one. MIP is for many. You can have 3 or 4 or n, but we'll stick with 2 here. And it looks just the same. We have a claim. It is given to the verifier and the provers. And then they can interact. The verifier can interact, ask them questions, and eventually should decide whether he believes them or not, and should err only with tiny probability. What's important here is that the provers can have designed a strategy as far as they want ahead of time, but once the verifier starts communicating with them, they are not communicating at all. They are separated. In this model, it turns out that every theorem has a zero knowledge to prove an interactive proofs without any assumptions. You don't need cryptography here. In a sense, physical separation of the provers replaces the computational assumptions. But I will not go more into this. I want to say that, like the previous model, we should ask whether this is reasonable. Well, I have two answers. One, it's only reasonable in real life. We know police procedures of separating two possible suspects in a crime into separate cells and interrogating them individually to see for inconsistencies. So at least in some parts of life, it is reasonable. It was also believed reasonable by our two institutions at the time, MIT and Hebrew University, who believed that it's it should be patented because probably it will be useful. And it was patented, not that anybody saw anything out of it. It was, yeah, but anyway, maybe it's reasonable. But again, it's fundamental in its impact, absolutely fundamental. And let me tell you about this. It's funny that I left this field more or less when we understood that we don't need cryptography for zero-knowledge proofs in these systems, but then other people did wonders with this proof system. So we have seen a hierarchy, NP, IP, 2IP, many IP, and we are basically asking how complex statements can we prove with randomness and interactions as we vary over these models. There were trivial inclusions that seemed really very generous. IP can certainly, not do anything outside of what can be computed in polynomial space. For 2IP, it was non-deterministic exponential time. But then, like, again, a year, I mean, this happened really fast. We had complete characterizations of the computational power of these proof systems. I will not read the statements. I just want to say that they all have very conceptual meanings. They are not just the usual acronyms of, like P and NP have very conceptual statements. IP equal P space has to do with being able to prove winning strategies as opposed to just existential quantifiers. 2IP equal next means that there are problems which are infeasible to compute, which can be verified by an efficient probabilistic verifier. And the last one, I'll tell you a little bit about it, is this PCP theorem. So let me talk about it. And all these theorems are normal mathematical theorems, and there are no assumptions, no cryptography, anything like that. What are PCPs? Let's see how I'm doing on time. Oh, I have 20 minutes, so that's very good. PCPs are acronym for probabilistically checkable proofs. They are a proof system that's non-interactive. They are very similar to NP, in which the prover just sends a message. So here's how it looks like, just in NP. A prover sends an argument to the verifier, but it's a probabilistic proof system, so the verifier can still toss coins and decide and must be correct with high probability on completeness and soundness. But you add one more limitation to the verifier. The verifier is not allowed to read more than 20 bits of the argument. Okay, I repeat, the verifier, in order to be able to successfully determine if the claim is true or not, can only look at a tiny, constant-sized portion of the argument. This looks maybe even more ridiculous than zero knowledge. I don't know your intuition. How are we going to find a bug in an argument which takes 100 pages? I mean, I don't know what is it doing now, but maybe it's trying the Riemann hypothesis. And if it produces at the end a 100-page document, how are we going to verify this, looking only at a constant number of bits of this, like one line in one page of these many books? I remind you that in the original proof of Fermat, there was a bug, and it was discovered by reading the whole proof. So what's going on? How can anybody even conceive of this? Let me tell you what's known. Again, there is a universality statement here. Every proof, every mathematical proof can be turned into a proof of this nature that can be verified just by glancing at it. And moreover, this transformation of a classical proof to a PCP is an efficient process. There is a simple algorithm that will do it for you and will not blow up the proof length by too much. This is a PCP theorem that I stated before. You can wonder about how can anything like this be true. And I think it's really nice that Madhusudan gave the talk about error correcting proofs, about coding theory and efficient error correcting codes. One thing they did not talk about is local decoding, which is he and others introduced into coding theory. That's very important, where you can catch errors in messages in error correcting proofs or decode parts of them by very local snapshots of the whole message, not by looking at the whole message. And a very similar but far more complicated thing is happening here. So you can think of it as a big brother of local error correcting codes. What are the impacts? Well, once we have an efficient version of this, really efficient, then our dream of referring papers in seconds will come true. But more fundamentally, this theorem had a huge impact on complexity theory in general, and in particular in optimization. For the first time, we were able to prove hardness of approximability results. So the analog of NP completeness for finding the optimum, we have hardness, NP hardness of approximating solutions to optimization problems. It's a huge advance. And it's a big field, and lots of other things I will not tell you about. It's absolutely a fundamental theorem of huge importance. Again, this is being, ideas are being implemented also in real life. Okay, so let me come to the very end of my talk and tell you about some more proof systems. So far, we've seen two types of probabilistic proof systems, or three, in particular, IP1 prover systems and two prover systems, and their characterizations. Now, we are going to change it again from probabilistic proof systems to quantum proof systems. Why? Because, again, proof systems are defined by verification algorithms. We added probabilistic algorithms to the verification. Now we have quantum. Why not add quantum algorithms to the verification process? I need to give you a one-page summary of quantum computing like I did with probabilistic one. Another axiom you can believe is that nature provides us with quantum phenomena. So again, people suggested, Manin and Feynman, that we build computers which use this. Namely, they are allowed to manipulate quantum superpositions using unitary operations like quantum mechanics allows us to do. What kind of computers we get? It took time to even formalize what a quantum Turing machine is and what is an efficient quantum machine, and but this was done. And moreover, it was quickly realized that quantum efficient Turing machines are at least as powerful as probabilistic ones. So we are gaining power in computation, at least it seems so. And then, you know, like volcano erupted. In 1994, Peter Shaw wrote his famous algorithm showing that this theoretical model of a quantum Turing machine can, in polynomial time, solve factoring and discrete logarithm problems. Why is this earth-shattering? Because these are the very problems that we use in order to establish security on, you know, cryptographic systems. So far, the machines on which this was possible is a theoretical machine, but you can imagine, and in fact, exactly what happened are frenzied attempts to do a lot of things, to develop supporting technology, namely build quantum computers. And this is something that companies and governments invest billions in. Friendly attempts to defend against these machines, if they come to exist, which is named post-quantum cryptography, change the assumptions, maybe instead of factoring and discrete log, use other hard problems. It's not so easy to find them, but we have some candidates, especially coming from lattice theory. Of course, people try to find more quantum algorithms for other problems. We were not that successful. We have a few more, but not many. And what we do have many of is new models. Again, the evolution of the field allows for different computational modes. And given that computation can allow quantum phenomena, we can allow verification. So let me tell you the last bit of the story I want to talk about quantum proof systems. So again, we allow the verifier to be an efficient quantum algorithm. So of course, the provers are infinitely powerful. They can be quantum as well. The first model was defined by Watrous. So just the analog of IP single prover, and I mark by star the fact that it is allowed to be quantum. What's the power of this proof system? It took about a decade to find, so it's far more complicated. Both prover and verifiers are quantum. It was not obvious, but it was found that it does not add power. It does not add power beyond probabilistic proof systems. So both are equal p-space. So that was one story. Then in this paper, people generalize the multi-prover interactive proofs to the quantum setting. And here, again, it took a long time, of course, using the previous results and using a lot of the classical PCP and interactive proof methodology and coding theory. We have this amazing result, which says that when you allow two or more provers, you can go far beyond the probabilistic two-proof systems. You can get so far beyond that you can even prove to a quantum verifier problems which are undecidable. So I repeat, this is RE, the class that Turing defined, the halting problem, or solutions to integer polynomials, or whatever your favorite undecidable problems are. They can be proven to a quantum verifier by two or more provers. This is stunning. This is bizarre. And you can maybe content yourself at this level, if you haven't seen the rest of the slide, that these complexity theorists, they play with weird objects and they get weird results, but what do we do with this? So here's something that came out of these papers. It had an amazing effect, and this effect is still in the making, in answering fundamental questions in math and physics. Already in this paper, they showed how it gives a negative solution to Wigderson problem, very basic problem in quantum information theory about entanglement, to the Korn's embedding conjecture in von Neumann algebra, and problems in group theory. And in fact, just last month, an announcement was made that quantum interactive proof systems can be used to refute the Alder-Slyams conjecture in probability theory or group theory, depends how you like. I will not talk about this. I will want to show you in the last two slides, in my last 5 minutes.
Oh, sorry, just to interrupt. It was supposed to be just about coming to an end now. So I don't know. So go ahead and finish, but
Okay.
go ahead.
So I can, yeah, okay, I can come to an end now. So I'll just tell you, sorry, that's my mistake. I will summarize it. The MIP star proof systems are ingrained in this idea that we allow quantum verification, but they connect to the fundamentals of quantum mechanics, and in particular, the Einstein-Podolsky-Rosen controversy about it, and their famous thought experiment, and to Bell inequalities, power of entanglement, and so on. So let me conclude. What have we seen? We've seen 50 shades of proofs or more, a variety of proof systems of all kinds. We saw that allowing interaction, randomness, and errors in proofs lead to very paradoxical proof systems. A comment I always like to make is, in many cases, these theoretical games we play enable advancement in science and math and society, like crypto, like quantum proofs, quantum computation. There are many connections between subdisciplines, especially on the last slide. And mostly what I want to demonstrate in this story is the evolution, which is very natural for the way we do, the way that the methodology of computational complexity leads us. So let me conclude with this, my favorite slide of this. If you want to know more on complexity, you are welcome to visit my website. It's free online. Thank you very much.
Thank you so much for that.